Hello, and welcome to this class. So I'm Laura Lewis, and we're talking about force diagrams today. Okay. So learning aims. It's an overview of the different types of forces, so a little bit of a recap on different types of forces you may encounter. An explanation of how we draw and represent forces in a free body force diagram. So maybe you may have seen that, it may be new to you. And a calculation of resultant forces and acceleration. So I'm going to push people a little bit. Okay, this one, it's not going to be too difficult. You'll be able to understand it, I'm sure. Okay, so let's sort of start out with a bit of revision here. So contact and non-contact forces. Okay, so this is from another video that I have presented, but obviously it's a good recap for the first bit of this video. So if you push a book along the table, you have friction on the book. You also have friction on the table. So friction's a contact force there because it's touching. Okay, so I'm just going to zoom out on this so you can write some things in. So let's look at a block on a table. So you've got a normal force is perpendicular to the surface, so it right angles to the surface in contact. So you've got a normal force. And this force, let's write that in. Okay, let's go through this together. We want to have to think about what it is before I write it in. Quick think. Pause video if you want to have a think. This is the force of weight. Okay, so it's force of weight. So it's mass times gravitational field strength is the weight. And remember that all forces are in newtons. Okay, all forces are in newtons. You'll come across that a bit more later in the video as well, but it's also newtons. This is representing the electrostatic force, okay, because the girl's hair has been attracted to these balloons. So it's actually a non-contact force because the balloons are attracted before touching. This is a person in a parachute, so shooting out of a plane. So air resistance is another force that we'll come across a lot, okay. Some of these you'll come across more than others. So air resistance is a very common force. Friction is a common force. Weight is a very common force, of course. So air resistance is actually contact because the air particles are touching you and touching the parachute. If you ride your bike really fast, you'll notice air resistance as a force, okay. And this is magnetism. So you've got two magnets attracting and repelling. So it's a non-contact. So that's magnetism. You've got tension in a rope, that's when I'm pulling it. So when it's tight, it's got tension. So you might see that as a force. And this one is representing a very, very common one as well, about gravitational force pulling something down. So even if you're not touching the Earth, it's the Earth's surface, say you're in an air balloon, hot air balloon like that, gravity is still acting on you, it's still pulling you down. Okay, so that's non-contact. You don't actually have to touch the Earth for it to be attracted. It's the mass of the planet which is attracting you, okay, and your mass which is attracting you to it. Okay, there's an overview of a few different forces. So you've got friction, you've got weight, so it's a force due to gravity on a mass. Got the normal force, or normal contact force, sometimes it's known, which helps us remember if it's contact, non-contact. Air resistance, very common. Magnetism, or electrostatic, tensional forces, and gravity. So you'll see some of those more than others, definitely. Okay, so let's have a look at this. So a force diagram. So on a free body diagrams, okay, so this one's drawn for you. Forces come in pairs. Okay, forces come in pairs. So you've got a driving force. This one hasn't mentioned yet, so that's good to start with that. Driving force, or force from the engines, it might be called. Okay, so that's all you need to know is driving force or force from the engines. It's 800 newtons to the left, that's unit of force. Weight, reaction force, so that's another name for the contact force. Sometimes it's called reaction or normal reaction or normal contact. They're all the same force. It just opposes the force of weight. Okay. Drag force. So yeah, only in physics, sometimes things are called different things, but they're the same thing. So always look it up. So reaction or normal contact or normal reaction, they're all the same force. Drag force. Drag again. It's another little example. Drag force, also another name for air resistance. Okay, so you've probably heard about that drag on an aeroplane or drag on a racing car. It's the air resistance, isn't it? So drag force, 450 newtons to the right. Okay, so you've got 800 newtons to the left. Drag force, 450 to the right. What would the resultant force here be? So let's do that together. Very simple, isn't it? So you've got 800 minus 450 Okay, so overall 350 newtons. Okay, that's easy enough to do, isn't it? So that's the resultant. Oh, what direction? So I need to put a direction. So the bigger force to the left, so the car would speed up. Have a look at this one. So on a bike, backwards reaction 30, forwards 100, resultant force. So about the capitals, and it's like sort of shouting, isn't it? It's meant to be noticeable on a big screen. So it's a textbooks. Yeah, I don't like capitals too much actually. So 100 is very even easier. This one, 100 newtons minus 30 newtons, 70 newtons. Okay, to the right or forwards. Okay, so you always need to write a direction as well. I'll keep writing it forwards. Okay, so these are all diagrams, all known as free body force diagrams. Okay, free body force. Any sort of diagram with just the forces on it. This free body force. So you could get this is from an exam actually. So it's a diagram represents horizontal forces. So this sort of direction, acting on a boat as it accelerates. So again, we've just got forces. The size of the resultant force is 2000. So it's a different way around this one. Okay, you could be asked like this, couldn't we? Let's get a text box. Okay, so we're told different things. So told the resultant force. Let's write that down. So resultant force equals 2,600. That's the overall force. Resultant means overall. Frictional forces. Still get friction from water. Okay, is 1,200 newtons. So it's asking us what the thrust is. So thrust is another word for force from the engine. So it's with engines. So the resultant force is 2,600, and the frictional forces, so that's going backwards 1,200. So thrust must be so we can write as an equation. Let's write an equation. Okay, so 2,000 to the overall equals thrust minus 1,200. So that means thrust must equal 2,600 plus 1,200, so that equals 3,800 newtons. Okay, yeah, they could be as big as that. It's a boat, it could be a big boat. Okay, so it's a different way of asking a question there. Okay, so it's a little bit more challenging, that one. Okay, but it's good to be challenged a little bit. Okay, so let's present on a bigger screen again now. Okay, so we can look at more detail and actually describe it very formally, but this is Newton's first law of motion. If the resultant force acting on an object is zero, so if the resultant, because so far we've calculated the resultant force to be a number, haven't we? But also resultant force can be zero. So if the resultant force equals to zero, there's two scenarios that could be occurring. So the object is stationary, so it means it isn't moving, and the object remains stationary. Or, this is the one people forget about a lot, the object is moving, the object continues to move at the same speed. So if it's already moving, so that's a car moving, okay, it continues to move at the same speed in the same direction. So the object continues to move at the same velocity, okay. So you've got some force to the right, same amount of force to the left. So if one's pushing one way and it's the same amount of pushing the other way, the net force, the overall force, is zero. Okay, so if the object was stationary, so there's a question here, the object is stationary and the resultant force is zero, what happens to the object? It will remain stationary, it will just stay sitting there. Okay, so explain this using Newton's law of motion. So yeah, so you could just write out if the resultant force acting on the object is zero, and the object is stationary, the object remains stationary, which means it sits there and doesn't go anywhere. Okay, even if you think about it, you had a box on the table and you're pushing with one arm, so one hand, and you're pushing with the other hand, but it's the same force, it's just going to sit there, isn't it? You have to have a resultant force. Okay, so this one is an object moving at a constant speed. So the car is moving at 60 miles per hour, not accelerating. It's not getting faster. Drag has increased. Okay, so drag's backwards. They're part of air resistance. Has increased equal thrust. So thrust is the force from the engines here. So the car is traveling at 60 miles per hour, and the resultant force is 0. What will happen to the object? Explain using Newton's law of motion. So the answer to that will be, if the resultant force acting on an object is 0, and the object is moving in this case, the object continues to move at the same speed in the same direction. So the object continues to move at the same velocity. Okay. So force diagram is a little bit more formally here. So when an object is acted on by more than one force, you can draw a free body force diagram to work out the resultant force on the object. So a free body force diagram shows the forces acting on an object without any other object. So yeah, if this is free body, it's just that one object. Okay, I mean, you see there could be objects around it and interacting, but you only show that one object. Okay, example. So we're going to sort of zoom out a little bit here. I'm going to draw a force diagram. So the cyclist in the picture is travelling at a constant velocity. Her muscles produce a driving force of 15 newtons. Draw an arrow on the diagram to show the size and direction of the overall resistive forces acting on the cyclist. So it says the cyclist is travelling at a constant velocity. So that means there's no resultant force. Let's draw an arrow. Okay, and it'll be equal opposite to this arrow here. Try and make it as equal as possible when you draw it, equal length as possible, and you write on. You have to write annotate. Annotate means to write letters on, or numbers, or words, whole words. So resistive force. Okay. Right, and also 15 newtons. Okay. So, and make sure the arrow is an arrow. Okay, so not just a line as an arrow. So maybe you want to make the arrow a little bit thicker. Okay, when you draw it. So a lot of time in exams or things, you'll be drawing it yourself. Oh, so always try and make it clear enough. Okay. Make it a little bit more shape outline. Here we go. A bit thicker. Okay, show that. So that's one example. Another example. Forces also act on objects when they fall through the air. There are two forces acting on this ball as it falls through the air. The weight is shown on the diagram. Draw a label, an arrow on the diagram to show the other force acting on the ball. So again, just draw something. So going through the air, so it would be air resistance, wouldn't it? Air resistance. Okay, air resistance. So simple enough, isn't it, so far? Okay, so quite appropriate for this week. So it's recording near bonfire night. So the rocket looks like a firework. Okay, so it says there is a resultant force on the rocket of 0.5 newtons upwards. Okay, so again, a little bit different way of asking this. It says the resultant force on the rocket of 0.5 newtons upwards when it takes off. The arrow on the diagram shows the size and direction of the force of gravity acting on the rocket when it takes off. That's gravity. Add another arrow to show that to the diagram to show the thrust produced by the burning fuel at the time the rocket takes off. You should label the arrow with the size of the thrust. So if the overall is 0.5 and this is 0.7, so let's write this out. Okay, so we've got resultant force . 0.5 newtons, and we've got gravity . 0.7 newtons. To work out the thrust, so the thrust. Get what the thrust be. So it's overall is 0.5 newtons. So 0.5 equals thrust minus gravity. So at gravity, we know that 0.7. So the thrust will have to be those two added together. 0.7 newtons plus 0.5 newtons, and that would equal 1.2 newtons. Okay, so when we draw that on, it's going to be going. So if we actually try and make it quite thick, let's make it quite nice and thick. Okay, a little bit longer. Oh, than the original. That's fine. It's because it's bigger than that one. That's why we're doing that. Into that text box again. So thrust 1.2 newtons. Right, let's see who answers that question. Right, let's present again. Okay. So something to think about now. So the car is moving to the right, so obviously you can pause this and think about yourself, but I'll give you a few seconds, I'll carry on. So the car is moving to the right to start off with. Okay, there are two opposing forces, 30 newtons of the engine, 30 newtons drag. Okay, so there's air resistance and friction. So what would happen to the car? So sort of stop, so you pause it and think about what would happen. Okay, I'm going to carry on. So the car actually moves at constant speed. So if you go back and see, look at Newton's first law. Okay, so you can tell the car is moving to the right, so it cannot stay stationary. That's one. Okay, car was to accelerate. The force on the right will need to be greater than the force. But we're just so just gonna make that a bit spaced a bit more out. Okay, so you can't really read that. Okay, so yeah, if the car was to accelerate, the force on the right would need to be greater than the force on the left. So this would need to be bigger for it to accelerate. If the car was to decelerate, the force on the left, so this would be greater than the force on the right. So it continues to move at a constant speed. So if you're puzzled by that, go back and look at Newton's first law we talked about. You see that if there is no resultant force and the car is already moving, or on the edge already moving, then it will continue to move at a constant speed. Okay. So there's two cars of equal mass having a race. The force pushing the cars forward is represented by the size of the arrows. Okay, so you could discuss. I mean, you might possibly be on your own there. Okay, you could work with someone else. Okay, so you can discuss what would happen to the two cars. What would happen? So if they both have the same mass and the force is greater here, car 2 will have greater acceleration. Think about pushing it. If you pushed a car with a bigger force, it would speed up quicker, wouldn't it? So car 2 will have a greater acceleration. There's more force pushing it forward. So the greater the force acting on an object, the greater the acceleration of that object. Okay, so you possibly on your own. So a man pushes a box on wheels with a force shown by the arrow. He then adds a box and pushes with the same force. What do we think would happen? Okay, so again, if it's lighter, you have less mass to push. It's like a trolley in a supermarket, isn't it? If you put more stuff in it, it's harder to push. So diagram 1 will have greater acceleration. So it's less mass to push forward. Therefore, less work will need to be done. So the greater the mass of the object, the smaller the acceleration of that object. Okay, so yeah, so same amount of force the man's pushing. If there's more mass, the acceleration will be less. So yeah, the big heavy trolley would be harder to push, wouldn't it? And if you pushed it with the same force as the light trolley in the supermarket, the light trolley would travel further and it would speed up quicker. Okay, so I'm going to full screen that. So going into Newton's second law of motion. So an object will remain stationary or maintain constant velocity if it is already moving, unless an unbalanced force acts on it, in which case. So it's a lot of writing for what we've just talked about. So the direction of the object's acceleration is the same as the direction of the unbalanced force. Okay, so if you're pushing forward, it's going to be acceleration going to be forward. Okay. The magnitude or size of the object's acceleration varies in direct proportion to the unbalanced force. So the more you push with the bigger force, the acceleration increases. Okay. And the magnitude of the object's acceleration is inversely proportional to the mass of the object. All that means is that if the object gets heavier, the acceleration gets less if the same force was applied. But yeah, you can kind of figure out we've got common sense and we've got real life examples. Okay, so a little bit of going into this a little bit. So how we say that is F equals ma. Okay, so you may use formula triangle if you like. So force in newtons, mass in kilograms, acceleration in meters per second squared. Acceleration's got the unit meters per second squared. So again, this is useful things to copy down. I'll just take a screenshot of. Okay, so it would be a good sort of practice to copy down this table and to fill it in. Okay, always you can go back to the slide before, so that slide, so leave it on there for a few seconds if you wanted to pause and screenshot and things like that, and also pause and screenshot that or copy it out. I'd copy it out, okay, and have a go at that equation. So it's sort of, yeah, it's pushing a bit, it's a little bit advanced, okay, but I think you probably would handle this. Okay, a bit of practice, it helps you to sort of get into equations. Okay, so if you want to do that. Okay, so check your answer and write improvement statement. So it doesn't mean you write the right one if you didn't answer correctly. So this is the correct way of doing it. Okay. So yeah, we're just all getting introduced to formulas at the moment. So just have a go at and if you're a little bit stuck, okay, go back to this slide. Okay, sorry, go back to this slide. Look at how you find these things and relate it to the table. Okay, so I'd like, yeah, that'd be a good exercise to do sort of independently. Okay, and also you can just check back and check at the answers. Okay, so thank you for joining this class. It'd be nice to see you in another class, and thank you for joining today. Thank you and goodbye.